Our speaker today is Professor Poi Anantrasirichai, who is Professor of Visual Computing at the School of Computer Science at the University of Bristol. So, Professor Anantrasirichai, I'll hand over to you now.
Thank you for having me. I'm gonna share my screen. First of all, I have to say that we also have Professor Juliet here, who will be more expertise on the InSAR or the data that I'm going to talk about. So as I'm myself in informed computer science, so it will be more about the I would say computer vision and that kind of thing. So if you have any questions about toward how to use deep learning to apply to this, so ask me. But if you have problems and the question toward to InSAR, so ask Juliet. Okay, so I'm gonna share my screen. Okay, so everyone seeing it fine. So the topic I'm talking today is, as I said, that we can apply computer vision to InSAR data specifically for volcanic unrest monitoring. Myself, the research is about the image processing, computer vision, and deep learning applied to challenging data. And InSAR will be one of them. So if you want to know more about other projects that I'm involved, so just feel free to get into my GitHub over there. This is what I'm going to talk about today. I have to say that normally I'm not create agenda for the talk, but specifically talk for today because it merges several things that using computer vision apply to the different application. So so it's quite nice to actually start with something that to see that what you could expect to hear about. So the first thing that I'm going to talking about how to use the binary classification for detect ground deformation, and then that will be fully supervised. And then when I move to the techniques that use semi-supervised learning, how to use with the massive data set. And then we also try to tackle this problem with unsupervised learning as well. So this would be for the anomaly detection. So basically we detect the deformation on the ground or volcano as the anomaly. And final topics would be about how to remove the atmosphere noise by using the image restoration techniques. So this is the brief say what is the data set that we use. So the technique we use is called InSAR, which is Interferometric Synthetic Aperture Radar. How that data create is that imagine that we have a satellite and then they kind of emit the radar signal and get into the earth and then it bounce back. So the satellite got the signal from the bounce back radar. And then they remember what happened there to actually create the images called SAR, which is synthetic aperture radar. And then when the satellite come back again, which is, for example, for Sentinel-1, 12 days later, so at the same position, so the radar is going down again and bounce back. So if nothing happened at all on the ground, so satellite should have exactly the same signal. Okay, so imagine it a clear, no atmosphere at all. But if the ground actually move, like in this picture, I hope you can see my mouse, the ground move. So when the signal bounce back, the satellite receive different phase. Okay, so when I know about it, so this is really clever. So basically, you can monitor all this ground change within like 12 days or more days by just to see the different interface. So because the way that acquired it look like a dense data, so you can the left one. Okay, this is what we acquired, the satellite acquired, is called wrapped interferogram. So the color you see here, well, vary between the red to the blue is the phase of this signal. So it's between minus pi to pi. So then what the Earth scientists doing? So then they unwrapped it with the the wavelength. So do you know that's actually how much the ground move? So like for example, in this example that you show picture here, so you can see that it move between move uplift for 10 centimeter within the time the satellite come back within that duration. Okay, so we use this to monitor what happened underneath volcanoes. For example, the picture they saw in the background is where Indonesia, that you can see there's some of the magma moving between volcano. Okay, so see, this is doing this slide from Juliet. So InSAR then have the good information that can be used to monitor the volcanic activity. So they found that if we monitor the ground and the ground is deformed, so the volcano move up or down, it's quite likely to link to eruption. And also that more than 50% that we use InSAR to detect the pre-eruption. So that's very kind of useful for monitoring. And we also use that to get the study what the magnetic system underneath the Earth. So you can see how the magma moves. So that would be useful to do that. So then the InSAR technique to be used, and luckily we have the great team of Cormac that they create the system called LIDA that acquire these interferograms, which is the 6 InSAR data, so around the Earth. So you can go to their portal and actually freely use. So they've already been trying to correct and copying the frames into particular for volcano to then we can study of that. So currently, I believe we have more than 2 million interferograms. So that become the problems that like we cannot manually go through all this. So another problem that I see in this before that it's quite easy to see if the ground move is the clear wrap of fringes here. But actually, when you're involved in the volcano, is that so around volcano they have a lot of water vapor because of vegetarian area. So meaning that even though the concept is very simple, that you can see fringes, that fringes tell you that the ground move, but in reality, in many cases, it's not very clear that what you see fringes is actually the ground actually move or it's from the atmosphere because of water vapor. So example that I show here that on the top row is the actual signal, that the definition that the something the volcano movement, but on the bottom row is that what you see in the data that actually the atmosphere. Of course, most of the time it's around volcanoes, so the atmosphere happen in the similar shape of the volcano, so quite similar to the volcano movement as well. So we tackle this by using, as I said before, they're going to be like binary classifier. So this is example that we have at Galapagos. So we use this to go through all of the image, and then wherever the output is more than 0.5 is flagged as the detect as the ground movement. So what we usually use the same similar here is so we have the input as the image, and output would be just like, is it deformed or not deformed? So it very straightforward application, the application for just binary classifier. So part of that, because it didn't have much time for labeling compared to if you have to get a bounding box. So just to get the image and then the label 1 or 0. And what we have to do is just like in the olden days, so when you do face detection, to get to go through all of these patches through like a for the whole images, and then just give the output at 1 or 0. But the main problems with this InSAR data, as I said, we have 2 million interferograms right now. However, I believe less than 10% that shows the deformation, or we call it positive, as the label as 1. So then we come up with the idea that actually we should use synthetic data sets. So then we can create more positive data. So here what we use, so we have 3 components which should happen in the real data set. So the first one is deformation. So we have different type of how the ground move, and then try to merge or everything. So then we can have the low brightness to the data, and combine with the stratified atmosphere. So this is happen when you have lots of water on the atmosphere. We have this data from the system called GACOS. And then another component of the atmosphere is the turbulence, which is where the temperature varying between the layer of the atmosphere. And then we combine them together. So then that means we know the ground truth because the D here, right? So then we know that exactly if this patch have D, have the deformation in that, it's become the positive patch. And if we use only S and T, so D becomes 0, that would be negative. So we can use that. So this is the framework that we tackle. This probably I think it's 2018 or 2019 that we create this framework. So basically, this is we use a CNN, which is AlexNet here. We use pre-trained model. So basically, we've closed this layer, the very first layer, because it's been trained by natural images, and then just let the fully connected or the final layer to learn about the signal, about the InSAR images. So we use here, we have the synthetic data and combined with the real data. This system in LIDA is from Sentinel-1, so we have to, so when you integrate the real sample, that would be have to get the model to learn the real characteristics. Because even though we combine all of these systems, sometimes it doesn't have the other sample, like such as noise, like, or the area that have the very low coherence. Okay, so after we train this, so we have initial with 10,000 interferograms with the positive signal and 10,000 without, and then we add about 5,000 more from the real data, and then we trained it. So after we trained it, we get this is the bottom one here is the prediction process or inference. So if we have real data, what happens? We have to divide into patches at the same size of we use for training for the CNN, and go to it and then label it, get the probability being 0 or 1, and then we merge it. And then we get the expression and then can include in the real sample for testing. So this will be deployed on the Comet Volcano portal. And the output that we've seen here is like having marked as where it's possible to have the ground deformation probability of that. So this is the portal that it deployed, so you can go then check and have a look. So we provide the information from the volcano, have the data from LIDA, and every time that it been flagged by this automatic machine learning using pre-trained AlexNet, it will show to show up on the different activity, and then you can go there and have a look. So it not only provide only the output from the deep learning, but also other information, because you also need to have the expert to check the time series and everything for that. So that's been used at that classic for quite some time. So how many years now? 7 years at least. So now the new era of the coming. So we're thinking, oh, maybe you should try transformer to see what it's like. So replace the CNN here with the transformer architecture. Okay. So what is transformer? Just in case that someone doesn't know or heard about it. So, but I'm pretty sure everyone have been using APU ChatGPT. So because that's the model that get with the transformer. Okay, so the transformer have the mechanism called self-attention. So for the convolutional layers, or that you have like defined kernel and filter, and then you update the weight to it more like a filter, right? But for the transformer, instead of doing that, it just look through all the possible of the data, and then try to relationship between each all the data in that in the whole set. So that's very useful for the language, basically. So if you, for example, if you say apple, you don't know it's actual apple that you can eat, or you apple it from the device. So you have to find out the context in there. It's like, I'm going to the Apple store, so now you know Apple actually mean the brand. So that would be that's why that they have used. So they have to find the relationship between all these words, and then to get attention to the word called apple. So for that word language I originally used for transformer, when it comes to for images, actually it's quite similar in terms of when we the first proposed using this as you divide the image into patches. So it's like each patch become one word. And then they get the transformer to try the correlation or relationship between these patches. And then when you train it related to specific tasks, so you will know that what is the keyword in that image that you should looking. For example, if you train the image for like interferogram to look at for the fringes, so the transformer to try to learn with this attention that the network should look at the fringes in the image. And then, however, the image is not the different image language image have the scale property. So you can see, for example, something you can see very close, something you say very far, even the same object, it could possibly be different size. So we have the new architecture we call swing transformer. So they call shift window. So basically to work in the way it's more like hierarchical. So then you have the scalability and also shift between the windows on that as well. So then we use this to try. So this is the result compared between CNN on swing transformer. We plot the result by on the x-axis, so when the short interferograms. So interferogram or InSAR, so you create between 2 times. They say that when the volcano come back, when the satellite come back, right? So it can create between 0 to 12 days. So 12 days or 6 days or 12 days for that. And this also can create the interferogram with the longer time, which is, for example, here we do the one that longer than 9 months. The way to how to get the longer time, so maybe Juliet can tell you better than me. So basically, you have several of the interferograms have shorter time, and then compensate between the each time then to get the longer one. So basically, if you're longer, that means you will have less effect of the atmosphere or noise, because you have several of the interferogram with a short one, and then the noise normally mean to cancel it out. So what it's telling here is, if you see this is the top 30 that been flagged. So if the volcano in the short interferogram, but it been flagged a lot, it could likely that if it's not the real signal, that means it have a lot of strong atmosphere, and the model may not be able to detect. But compare between these two, because it's a lots of the interferogram that have been flagged, so we not actually be able to get through of them. But at least I can show you for some example that what happened to compare between CNN and SWIN. So the top one, you can see that from the volcano, that a SWIN transformer seem to detect less. It's actually the signal there. So this implies that CNN have the ability to detect the fringes that not complete as around better than transformer. And I actually we also found that actually CNN probably detect a smaller signal better than CNN as well, but better than the transformer as well. However, transformer is better to detect in terms of if you have noise that interfere the whole image, the whole fringes. It's quite likely that because of the way that have the attention mechanism, that because you go through all the possible, so then why the thing then only go to the local patch, right? So that means even though they have noise interfere, so they give better result. Another thing that we found is that for transformer is better to, in terms of the ignore the atmosphere that look like lots of fringes like this. Okay. So that for transformer. So then we move on to the semi-supervised learning. So part of that, because we have so many data at unlevel and almost impossible that we get the expert to level for us. So the semi-supervised learning, the way it works, that you have the task that be labeled, but with a small number being labeled. And for unlabeled data, you have another model to learn the structure inside the these lots of data. Usually the same way on the and if we call it foundation model or ChatGPT, that been learned by itself for the lots of languages. So the way that we use, which is also the same as many people are they're using for the unsupervised learning, which we call contrastive learning. Which is also the same as the ChatGPT or any other language model. So the concept is that you have a loss function that be able to tell that if the image, the two images that have the quite similar or the same thing, the distance between them in the feature space should be close. So like the dog and between the dogs. But if the between a dog and cat, so that similarity should be low. That means the distance is higher. Okay, so that the concept of the contrastive learning. And the way that we use, we call DETCO. So how you train this model is that you feed the image, and then you augment it in several ways. So you also like change the color, crop it, and then patches. So because these patches and augmented data come from the same image, so similarity should be low, should be high. So the loss function should be low. So that the concept how to use contrastive, and then you put lots of data in there, and eventually the model will be able to learn that okay, this is come from the dog, which is the same type. It come the cat, it's a different type of the dog. So what we tested here that so we use that unsupervised and contrastive learning here, which is probably now we call foundation models, but we didn't use it in that time that I tried. After we have that, we use that to train the ResNet and get that as a pre-trained features, and then use the downstream for the detect the fringes. Okay, so for the downstream now, because we label only like 100 levels, so we could be used as a traditional other object detection, which in bounding box. So we can now be able to do it like get the corner or location of the fringes in from the large model. So what we use here, or you probably have seen this before, when you do object detection, so do it normally, it's probably easy to find it here. So you have the features, and then they define the proposal that go to the area that could possibly have the objects there, and then also classify what type of the objects as well. Okay, you probably heard about YOLO. So YOLO is probably the most popular one that been using these days for object detection because it's very fast. And that to be also used for satellite data a lot as well. This is, for example, used from SAR to try to detect a ship from on the sea. So currently, I believe that it show here that they use YOLO version 4, but now probably version 11 or 12 already, so make it faster, better, and using the transformer as well. So we use that as a downstream, and then we detect. So this is a little bit control because we want to compare with the supervised learning at how of these use the semi-supervised perform compared to the supervised one. Just remind you that for supervised, we train on the 15,000 this uses synthetic data, but for semi-supervised, we didn't use synthetic data at all. So we just use the unsupervised contrastive learning to learn the patterns of the images in there. So when it come to the strong signal, so both of them detected correctly. There are some false positives for both model. That because the fringes is very clear, and as I mentioned before, the atmosphere is really look like the shape of the volcano, so it's so difficult to distinguish. There are also some false negative from the semi-supervised learning because some of the very small signal not be able to detect. But we also found that for the atmosphere, the semi-supervised seem to be able to ignore it or discard it from the or distinguish between the atmosphere and the deformation quite well. That example will show here that the in supervised detect these fringes as the deformation, but ignore for that. So now, because we have like and I said lots of learning, finally we try to tackle this problem as anomaly detection. Which we've been using a lot in the other applications before, like for example, we show here about medical data or also natural data. So basically what happened is that we created a network that learn like a normal statistics of the data that you have. And anything that out of this distribution will be flagged as the outlier or anomalies. So the easiest way to do for the images that you use autoencoder. So you have encoder and decoder here, and when you feed the input as the image in, and we try to force the autoencoder to generate exactly the same image. Okay, so they have loss function compared between the two. They should be very similar. So when you detect the anomaly, meaning that if you have something coming in and then it generated, which it should be when it generates to be the same as other normal distribution. So the image, the input and output, if it's too much different, that means there are some outliers contained in the input image. But that's the autoencoder decoder, but we actually use the variation in autoencoder, which is the more sophisticated way to learn to generate exactly the same image by forcing what we call it the latent space or feature in the middle here to be like multivariate of the Gaussians. So you forced to say that, okay, most because it had lots of data, so it's quite likely that these data will come from several of the Gaussian distribution. So instead we define the mean and the variance of the Gaussian distribution instead, but you didn't actually define only one because it's multivariate, so they have defined it could be 100 of the distribution as well to learn. So the first attempt that used that we input this and then try to find the different distance between the original one and the reconstructed one. So if it's very close, that means the distance is very small. So they can see from this histogram. And if the generated one have to quite different, so that means it could be likely to be deformation ground. And so we use this method and then put some, because it's from synthetic data, so right, so then you can define the threshold and then use it to run to the global data set. And we found some of the deformation that we never find it in using the supervised learning, and we deployed it before. So that means when you use this to learn the normal distribution, and that's the beauty of the unsupervised learning, that we learn more of the characteristic of the data instead of like in supervised learning, you only learn from the training data you test on. And then we tackle this about using the patch distribution, because that's the whole image. So instead of the using the autoencoder as the presented in last slide, so this is a PhD student that instead he used the pre-trained model. Instead, extract all the features and then plot the distribution of these features instead. But the same idea that, okay, if we found the anomaly and then we extract the feature, that feature should be outside this distribution. So then the way that detect the anomaly will be the same. So it depends on the distance of the threshold that we define. And this is the result that he got. So he basically trained with the period that we know that the volcano is quite stable. And then we test it on because we know that there's some of the activity that happened. So this compared the top row that you can see is the specific volcano compared between the supervised and unsupervised. So the top row is from unsupervised from his method. So this learned specifically for each volcano though, but it's the time series, so it's more in the previous time. So you learn more characteristic of that. And we found that the anomaly is very good in detecting something that is not in the supervised the training data, but in the supervised learning. For example, is some of the large atmosphere that can say, oh, this is because it's been learned for the from the time that it never stable. So, but because this never include in the training is supervised, so it's a bit flat because a lot of the it's the way around actually. So so it been flat because it's something wrong with the what's it called, how to process it. For example, in here as well, because it's a lot of fringes in lab with that's the wrong processing. And another way that I'm trying to tackle this is how about we doing the atmosphere denoising, because that's the main problems for this volcano detection. Basically now we use the thing that cost vision, but sometimes it's probably not quite right. So we want to know if deep learning can help with that. So what we use is the thing like the same technique as using the image restoration. So you can see that we use this network to do like deburring, denoising, derain, and super resolution here. Most of the network that you probably already know is like UNet. So UNet actually originally proposed for the medical image segmentation, but now we use for almost everything about the image restoration. And the newer architecture we call GAN, which is the generative advisory network. So we use UNet here as a generative model here, but also have another network to say, or you to say that they to classify, try to predict that what this generation is the real image or not real. So in this way, that how to learn. So this discriminator will force the generator to make the real data, to close to the real data. So the first one that we attempt, we use the restormer. So this can see it's the same as the unit shape here, but replace the convolutional layers with the transformer. And the second one that we tried called swing transformer. This is the similar to the one that we use for volcano detection that I mentioned before. But instead of doing the unit style, we could just repeat it, use a lot of layers of the swing transformer. We can look at here. They look like the ResNet. I'm not sure that you heard about it. So it's the way that you have the skip layer every now and then. So then the back propagation you can learn better. And the last one that we try use the diffusion model. So diffusion model is the originally it used for generate image. So like if you shut the diffusion, ask them to generate a cat. So that with the way that they use this stable diffusion to generate a cat. But at the same time, you can use it as a conditioning. So what the diffusion model is doing, so then first you diffuse the image into the noise and try to get this unit style learned it to basically get the noise back to the image that you want to do. But when you kind of have the conditioning, so we say that, oh, do actually want cat to be in the middle, so you can draw it and make a condition into the network to learn it. So we using that but instead of use the noise like a Gaussian noise, so we use turbulent noise to diffuse that instead, because it's more close to the problems. And then we use the start date, end date, DM, which is the topography, that how the volcano shape, and use the interferogram as the condition to make to see if the output should be the clean image. This is example of the result that we got. So we try on the Lagrange model to have the 4 GPS station and use that as a golden standard basically. So the GPS will be ground truth and then compared to what we deal with the satellite images. So if you didn't do anything to the raw data, I mean that get it from the satellite, it compare the mean it's not mean square mean absolute error, lower is better, and you get a higher number there. Time series is actually the method that a scientist use. So maybe Juliet explain me better than this. So they have the several of the interferograms, and then you kind of unwrap reverse back to create the longer time series of each point of what the ground move. But I believe that this time series that we got information here, they come from the interferogram that already been using GAR-COS for correction as well. And this is the 3 network that we try using deep learning. So far from the what we initial result that we got, so we would say that Restormer probably not the good one to use, but spin IR give it the best result in terms of mean absolute error. For the diffusion, they're pretty quite good in the station that actually closer to the where the ground is deformed. And we found that the diffusion model probably also underestimated as well. But one thing that I probably would like to mention is that the mean absolute error probably not the right metrics to measure. So this is what we actually found, because most of the time the data is stable. I have lots of the ground is moved basically. So the most of the time the data that we train, they have a 0 in there. So this is the station PUEL. So it's about here that have some the deform. So the GPS, this is the ground would we have, and then the y-axis is the where the model predict. So even those we are the provide quite good mean absolute error, but it turns out that most of the time they predicted at 0. So meaning it actually probably not the right method to use for that, even though they seem to give quite good absolute error. We're still working on this. Hopefully they get better though, and hopefully we get the DM to get close to the LIDA, that mean or the prediction and align with the GPS. But this could be also mean that they have to change some loss function and make sure that the data to be trained to be suitable as well. So I didn't say, I didn't mean to have this, but I think it's quite nice that what the last application that we try to tackle right now, we got a new PhD student start working on a face unwrapping. So we want to see if we can use deep learning as the inverse problem. So basically what we have here is wrap input. So we can have the wrap input here, and to see if we can have the network that learns some parameter and be able to unwrap it properly. I would say this early work, and many people actually try to do that, but it's not very successful in terms of using deep learning, because the real data is actually not as clean as the method that they use for train. So for example, this is the result that we got. You can see that the real surface that after unwrap, this is the input, and this is the output should be, but this is the actual output. And some of the signal actually disappear, for example, from here, because the network that we use, maybe it tried to be over smooth. So this still early work. So we want to improve this. Maybe we can loss function a bit more attention to the fringes more, for example, or using the histogram here for as another loss function. And we're also trying to use the diffusion model as well, so then to reconstruct all of these problems. But that early work, and hopefully we get use some update if we get some more result. So that's it for me. If you have any question, I'm happy to take. Hopefully it's not too much information here.
Do we have any questions for wait? Okay, I've got a question. Can you hear me online okay, or should I?
Can you speak louder? That would be nice.
Yeah, that was a really interesting presentation. Lots and lots of different methods you tried. I was just wondering, when you mentioned some of the differences in the performance of the the movement detection methods with the different supervised and unsupervised methods. Did you see the same trends when you looked just on synthetic data as when you looked on real data? The reason I'm asking is because I think the sample size for the real data is relatively small. So I'm just wondering if you saw the same trends on synthetic data.
Interesting question, because when we tested, we didn't test it on the synthetic data. So we didn't actually have that particular answer. However, I would say that because we didn't, like I said, in synthetic data, we didn't include, like, for example, this, did it show here? For example, we didn't include like these fringes in the synthetic data.
Yeah.
So that wouldn't come up for that. So synthetic data is not as generalized as the real data. That's why we try to move on to the unsupervised learning or semi-supervised learning to use more information that you cannot create in synthetic data. But however, we can, if we want to update the model at some point, we could include all kind of this negative sample into the model, and that model will learn better for that. Yeah.
I see. Thanks. So I was wondering then, what do you think what are like your main like next steps? Do you think it's worth staying with the supervised methods, or do you think unsupervised is going to be the best going forward?
Well, part of that, if to be honest with you, if all the expert label the data for us,
yeah,
supervised always better, right?
yeah.
But also nobody can go to, yeah, I'm really appreciate when they go to like 1,000 images already. So very hard. So that unfortunately that the way it works that you have to go to the unsupervised learning. Similar way in a lot of the large language model, because nobody actually label where is the word for you, right? So they have to get the network to try to learn the patterns within the data that not be able to label. And that will be the future of almost everything that we have lots of data. It's in not only satellite, including medical images as well. Like we have lots of data, but nobody can label it, so that you have to come up with a way that to make it self-learning. And then we fine-tune it afterward as a downstream to make that model that been trained from the unsupervised learning to be able to perform the task that you want it to be. Yeah.
Yeah. Oh, thank you very much. Thank you.
Thank you.
Got a question. Can you hear me?
Yes.
It was a really nice presentation, thank you. In terms of the semi-supervised learning, is contrastive learning the only approach to take? Or are there other ways to go about doing semi-supervised learning?
No, actually not. There's several other things that you can use. Okay. Yeah, but because of the way that we tackled it, because we separate into the unsupervised and then with the small label data, right? So then the unsupervised, it been proof that even though it's, to be honest with you, even though it's say contrastive learning, there are so many methods. It's a concept actually. The contrastive learning, the concept that okay, if it's similar, you produce the low loss with a high with a close distance, and then if you're not similar, you have the higher loss. So that's the concept. But the way to do it is so many ways. So, like for example, deco is one of the method how to use this concept. Yeah.
Interesting. Thank you.
Thank you.
Hello.
Hello.
I want to know what support can we give to the model to make it better predict the outcome, the results. I'm not I'm a student of computer science, so that's my interest.
So the way that normally improve, so either you change architecture, right, or use chain loss function to get to make sure the loss function to get the model behave the task that you want. The same as what they say. So you have the unsupervised learning, the train on a contrastive learning, and then you have downstream. The downstream task will be controlled by loss function that make sure that the loss function, the model, the downstream task behave the what you want. And another thing that now is very popular that for the what to say, to cut in not the natural images, so like a satellite or medical, so we integrate some knowledge or like physics it there because it's been studied for a really long time, more than deep learning, right? So then they know some model and then how to use those information integrated into the system. The most of the time will be loss function to make sure that the way that they learn that agree with the physics that have been studied for 100 years. Yeah, that would be my answer. So how can I improve it? That if you know some physics knowledge to integrate that in that would be the best. Yeah.
Oh, so does it mean that the solution is about adding more knowledge, not about refine the model or the architecture itself?
So that's the what I mean. So when you want to refine it, how you going to refine it, right? So the way that you refine it, it's better to have more information that you can provide. Otherwise, you cannot refine it.
Yeah. Okay.
Right. So that's what I mean. So yeah. So then you refine it with the new information or force it to learn what it should learn. So basically, it's like you teach baby to walk in the way that it should walk.
Okay.
Yeah.
Thank you.
So one thing I have to mention that even though you change architecture, it doesn't mean that larger architecture will be always better than smaller one.
Yeah.
So for example, the one that we use for detect fringes. So we try on that. Why we end up with AlexNet, which is a very small model compared to VGG or the GoogleNet, for example, because with the way you learn the data, the problem, you just learn fringes. So it doesn't, the semantic on it is only one thing compared to if you learn a natural image like cat, dog, or they can running around in many different background. So that will be more complex. That's why they have more non-linearity of the distribution for those natural image. But to detect fringes, so smaller architecture is better. So yeah, it depends on the application that you want to tackle. Yeah.
Yeah. Thank you.
Thank you.
Yeah, sure.
So just another question, just to expand on the previous point, is there sort of, have you explored adding physics, and what type of physics would you be thinking of sort of using or adding to the work that you're doing if you've explored?
Interesting questions. This is always in our mind. So we've been talking with Julia for quite some time, but we haven't actually managed to start it with yet. We need more students basically. But we did try one thing that, for example, which one? With diffusion model, let's say here. So instead of only generate it and then try to get the image work, we also want to learn what parameters of the model. So basically, if we know exactly the synthetic data created from Morgi model with this equation, would that possible to force the network to generate that parameters and then compare to the real parameters that we already know because it's synthetic data, and that will force the network to learn a particular type. I used it for different applications. I have another the project that's doing the low light denoising, and we know what type of camera, and then we used another network to try to force it to learn what type of the noise to help denoising basically, and that helped. Yeah.
Thank you.
It's okay.
Okay, I have just one more question. So as you mentioned in your presentation, these image processing techniques, they have applications in a lot of fields, including medicine. And you have experience of several of these fields. Would you say that there are any unique properties of the InSAR data which are you have to take into account when using deep learning?
Yeah. Yes. First of all, the noise is very different. So the noise in the natural images and the noise in medical images is more random. Even though it's not totally random, but it's more random than the turbulence, let's say here in the because the noise here is more interfere like propagate of the delay of the radar. So it's more spatial correlation. So that's why the denoising is, I would consider this problem in fact is more difficult than natural images because of the turbulent noise. It's spatial correlate, and the data itself as well is very skewed. So you can see that as I said, the deformation signal is less than 10%. Okay, so that means we have loads of the data that not actually deform, but it's so variety in terms of the atmospheric characteristic for those regions. And also because it's the of the Earth, so then they also have a seasoning coming as well. So there's so many factors that totally different from other images. Like for medical images, for example, they have lots of data, but most of them actually acquired from the both patient. So you actually have lots of the positive signals there. And then they just have to request someone that don't have those particular problems, so then have kind of balanced data set, let's say. So the data set is not skewed as the satellite data. Yeah. Does that answer your question?
Yes, it does. Thank you very much. Okay, if we don't have any more questions, let's thank our speaker one more time.
Thank you, and hopefully that'll be useful. And if you have any more questions, just send me email. That's fine.
Okay, thank you very much. Thank you.
Thank you.